Hi, Slava.
Hello.
Hello. Hi. Nice to see you.
Yes,
Nice.
the same. Hello, Birkar.
Hello. I'm just trying to share my slides.
Maybe I will say a few words before I talk.
Yes, sure. Can you see the slides?
Our host is Jim Jong, so he should say when we start.
Yeah, we could see your slide. Yeah. Nice to meet you.
Okay, that's good.
Yeah, so
We start.
shall we start now or?
Yeah, we can start anytime you like.
Okay. And so I will say a few words about before. It's very briefly. And so Caucher Birkar is national from Kurdistan. And even in his name, you can see this because Caucher Birkar means mathematician migrants in Kurdish. And so he has undergraduate, he is from very simple family, we can say, from farmer. And he studied his undergraduate, as a undergraduate student, he has been in very good university. It's Tehran University in Iran. It's very, we had before very strong students also in John Hopkins from Tehran. And then he had a graduate studies in Nottingham University in the United Kingdom, where we met with him. And a few years later, when he got his PhD, his triumphant entry to rational geometry started with a paper with Birkar, Cassini, Haken, and McKernan. And later he continued with very strong papers, especially his very famous papers related to M complements and related to Borisov's conjectures and Alexiev conjecture. And I would like to say also in addition to this talk, that his PhD was related to sort of technical question, epsilon complement. And some readers complain that it's very difficult to read or something. But this is not a problem of Birkar. It was a problem of a subject, because it's still, the subject is not very settled. And today he will talk about current state of birational geometry, and maybe it's a little bit clear situation about complements now, at least usual log canonical not, and some application to birational, other application to birational geometry. Okay, so here you are.
Okay, thank you very much for the kind introduction, and thank you for the invitation to give these talks. So in these 3 lectures, as Slava suggested, I'll try to give an overview of not only birational geometry, but in general, the classification theory of algebraic varieties. And this sits at the very heart of algebraic geometry. But in the first lecture, I'll try to give a very general framework. I don't want to go into any technicalities, so a lot of details will be omitted, and a lot of results, and even a lot of people will not be even mentioned, unfortunately. But in the second and the third lecture, I will go into more technical details and focus on some part of this story. Okay, let me start with ancient history. I just try to trace where algebraic geometry started, basically in the ancient world. Babylonian mathematicians, they could solve equations about 4,000 years ago. They understood already quadratic equations. So let me just tell you in a simple setting how these kind of problems emerged in their setting, why they got interested in these kind of problems. As far as I know, it was related to applications, to real world applications. They just try to understand certain things in the real world, and they came up with equations. So for example, suppose that we have a rectangle with length t and width s. There is a typo here. I changed the notation, so this is supposed to be t and s. Suppose that we have a rectangle with these sides, and assume that we already know the sum of the sides. So let's say x plus y, which is here the same as t plus s, is equal to some number a. So we know what a is, but for the moment we don't know what t and s are. And suppose also that we know the product of the length of the sides. So we know t plus s and we know t times s. Now we want to find out what s and t are. Obviously, this is a mathematical question. Now, if we do a little bit of manipulations here, if we write down s in terms of t, then using the equations we have, we come up with something like this: t plus t over t equals a, which in turn, if you multiply by t, it gives you this quadratic equation, t squared minus at plus b equal to 0. So we know a and b. Now we want to find out what t is. And if we know what t is, then we can also get s from this equation. So this is obviously a degree 2 equation in one variable. And this is a picture of a text from thousands of years ago. And I suppose that it talks about this kind of equation, although I'm not completely sure. But anyway, this makes it clear why they were interested in equations in the first place. It had to do with applications with real world kind of problems. And they knew how to solve these kind of equations. Now, later mathematicians, they try to solve equations of higher degree. So it's very natural if you are curious to see what happens if your equation has degree 3 or 4 or higher. So this took thousands of years to understand. Now suppose that kt is the set of polynomials in a variable t with coefficients in some field k. For the moment, we can just assume k is like the rational numbers or even the integers. And suppose that we have an equation f in kt, so we want to find the solutions of this polynomial. Because the first question is whether there is any solution at all or not. And that question, of course, depends on the field that we are working with here. For example, if we work with a complex number field, then the fundamental theorem of algebra tells you that, of course, f has solutions and you can decompose it into a product, where the components of the product will just give you the solution. But if you work over the rational numbers, that may not be possible. F may not have any solution. If you work over the real numbers, you have a better chance of finding solutions. So it depends on the kind of field that you are working in. Over the complex numbers, for example, quadratic equations can be solved. Now, the thing here is that we are not only interested in the fact that whether this equation has a solution or not, but also writing the solution down in a kind of precise way using some formulas. So in the case of quadratic equations, we can find the solutions just by this plugging into this kind of formulas. So this formula only involves radicals, like taking roots, maybe second root or higher roots. And people just try to understand whether you can do the same in higher degrees or not. So if your polynomial f is arbitrary, let's say over the complex numbers or over rational numbers, can you write down all the solutions in a precise way, similar to this degree 2 case or not? And of course, it took thousands of years to understand. And then finally, Galois theory in the 19th century tells you that, yes, you can do that if the degree is at most 4, but not otherwise. And so this question of writing down the solutions or whether solutions exist or not led to something really beautiful. So Galois theory is one of the most beautiful examples of modern mathematics. That's quite different from maybe the classical kind of mathematics. So you see that even in the most simple settings, we get something that's quite interesting. So you know that in undergraduate, usually departments spend a whole course on this topic, Galois theory, just to understand polynomials in one variable. Now, on the other hand, in a different direction, Apollonius classified intersections of a plane with a cone. And this happened in the 3rd century BC. So people before him were also interested in this kind of geometric objects, but I guess he wrote a book and then he did this more systematically. So if you have a cone and if you intersect it with a plane, what kind of shape do you get? So there are many different possibilities. You could get a circle, you could get an ellipse, parabola, or hyperbola. So in this picture, you don't see the other half of the cone. So the cone is actually supposed to have another half sitting on top. In that case, for example, you can see more because the plane can intersect the upper part also. So you will see more. So this is quite interesting because later, many centuries later, people realized that these kind of shapes, they are given by quadratic equations of degree 2 in the plane in the setting of analytic geometry developed by Descartes and other people. And in a way, this problem is actually this kind of consideration is quite natural and even intuitive. For example, last year I asked my little boy that if you have a cone made of cheese and if you cut it like straight with a knife, what kind of shape you get? And he immediately told me a circle. So this is quite intuitive. And then I asked him, what kind of shape do you get if you cut it with an angle? And then he told me you get an oval. So this is something that even little kids can understand. Now, in a different direction, Diophantus, he studied equations over the integers. And this happened in the 3rd century. So again, it's kind of the ancient world. So what he wanted to understand was if you take equations maybe in one variable or even more variable, maybe 2 or 3, and then the integers, the coefficients are all integers, what kind of integer solutions can you find, whether there is any solution or not? And Fermat studied this kind of equations much later. And of course, other people also, but Fermat is quite famous. So for example, one of the things we can look at is an equation of this form. Let's say you have 3 variables and this polynomial t1 squared plus t2 squared plus t3 squared is a polynomial over the integers. And then you can ask whether this has any solution over the integers or not. And you can see immediately that there is only one trivial solution because all these things are squares. So if the sum is equal to 0, all this should be 0. Therefore, the only solution is 0, 0, 0. So this is not very interesting. But if we now change this plus t3 squared to minus t3 squared. So we have the same equation, but I just changed one of the pluses to minus. And then we will have a lot of solutions, in fact, infinitely many solutions. And the solutions of these equations are known as the Pythagorean triples. This equation was, in fact, already studied by the Babylonians, maybe not in a kind of formal setting, but they already knew this Pythagorean triple, that you have 3 numbers satisfying this kind of equation. They had like a list of these numbers, and some of the numbers were quite large. However, if you change the equations just a little bit, then you can end up with very complicated equations. For example, if I change the second equation, replace the power 2 by a higher number, let's say m, so we have t1 to the m plus t2 to the m minus t3 to the m, where the m is at least 3, and then you can ask whether they have any solutions over the integers or not, and it turns out that it has only trivial solutions. By trivial, I mean that one of the solution should be equal to 0, one of the coordinates. And that is, of course, Fermat's last theorem. So just playing with equations, even simple ones, can give you very complicated problems. Now, all these things happened before algebraic geometry maybe was formulated as a subject. So that's like prehistory. Now then we can ask, what is algebraic geometry? We can define algebraic geometry in very simple and imprecise way by saying that algebraic geometry is the study of solutions of systems of polynomial equations and all the geometric structures that comes out of this kind of systems of equations. So that's the easiest way of defining what algebraic geometry is. But of course, if you don't go into the subject, this can be very misleading because you probably think that we are just playing with equations. Although you could be doing algebraic geometry for years without dealing with even one single explicit equation. Now, the subject is related to many parts of mathematics and also outside mathematics, like mathematical physics, computer science, and these days it finds applications in many other areas like biology, economics, and so on. But I'm not going to talk about those things. I will just focus on the very center of algebraic geometry. So if you want to do algebraic geometry, you need to start with choosing a field, K. And the most important cases are when you take K to be the rational numbers, real numbers, complex numbers, or finite fields, or algebraic closures, for example, of finite fields. But in this talk, I will, for simplicity, just restrict myself to the case of complex numbers. And if there is time at the very end of the lecture, which I doubt, I will say a few things about the case of rational coefficients. So for the moment, just assume that we are working over the complex numbers. Now, to define the main objects in algebraic geometry, we start usually with the local picture. And in a way, I want to do something quite similar to what happens in differential geometry, that you maybe study disks, and then you glue this together to make a manifold. So in algebraic geometry, we have something similar, although there are a lot of differences. First, we start with a polynomial ring over our field. In this case, K is the complex numbers. And then, so this is the algebra. The polynomial ring is the algebraic side, and we also need geometry. An affine variety is the common solutions of a collection of polynomials in this polynomial ring. To write it more precisely, X, the affine variety, is a set of points where the points have coordinates in the field A1 to the AN, such that if we put in these coordinates into all these polynomials, they all vanish at the same time. So we are considering here the solutions as points with coordinate in K, and therefore we can consider these points as points inside K to the N. For example, if you take the real numbers, K to be the real numbers, then let's say N is equal to 2, then your point will be in the plane, just K squared or R squared. Now, everything about this object, this geometric object X, is encoded in the ring, the polynomial ring divided by the ideal generated by this collection of polynomials. And that's where the name algebraic geometry comes from. On one side, you have algebra. On the other side, you have geometry. And there is a precise dictionary. You can go from the geometry to the algebra or from the algebra to the geometry. And the advantage of this setting is that you can use the algebra to do everything very precisely, but you can use the geometry, you can use your intuition to so that you can say where you should go next. If you just work with algebra, it's difficult to get a direction. Maybe it's easy to prove things because it's precise, but the geometry tells you what you should do next. So a very simple example of an affine variety is the variety defined by this equation, just t2 minus t1 squared. And this defines a parabola in the plane A2. If we take, let's say, for example, if you take the picture over the real numbers, then we just get what we get one of the examples of Apollonius, one of the conic intersections. On the other hand, if we take t1 squared plus t2 squared minus 1, this defines the circle. This is another example of these conic sections. Okay, let me also just give you something a bit more complicated. If I take the equation t1 to the 3 minus t1 plus t2 squared minus c3, and so this defines a variety inside A3, and the picture over the real numbers will look like something like this. It's almost similar to some kind of chair or some kind of seat. But of course, we are working over the complex numbers, so you don't really see the actual picture, because that will give you something which has dimension 4 with respect to the real numbers. And we can't see something of dimension 4. But at least we can see a slice of the actual picture. And this is the slice over the real numbers. This, in fact, even if you just draw pictures over the real numbers, sometimes it gives you some ideas of what is happening and what you should do next, especially in lower dimension. Now, that was the local side of the story, but we also need a global version of this, a compact setting. To define the compact setting, we need to work in a slightly different space. If you just work in these affine spaces, like in the plane or in the three-dimensional space, what happens is that your objects locally there is okay, but the problem is that you usually have something going on at the infinity, and you can't see that. For example, if you have two lines in the plane, of course, we have learned that two lines in the plane, if they are parallel, they don't intersect. However, when you go to this compact world, to the projective setting, these two lines, in fact, intersect, but the intersection happens to be at the infinity that you can't see. So that's why we like to go into this projective setting. Now, the n-dimensional projective space itself is defined as the set of points where we have now n+1 coordinates instead of n coordinates. There is some assumptions here to make that at least one of the coordinates should not be equal to 0. And these points are determined up to this equivalence, that if you have a point and if you multiply all the coordinates with something non-zero, then the point will stay the same. But this is quite different from the affine, the usual n-dimensional spaces. So in the projective setting, coordinates are not uniquely determined. They are determined only up to some multiplication by some scalar. But it happens, if you just look at it a little bit, play with it, you see that this Pn is in fact exactly an. An is just k to the n, and then union with a hyperplane at the infinity. So for example, if you have a P1, then that will be just A1 together with one point at the infinity. So that's why this is a compactification of the usual n-dimensional space. And then once we have this ambient projective space, we can define projective varieties, similar to the affine case. A projective variety in Pn is the set of solutions of a collection of homogeneous polynomials. You have to take homogeneous here. Homogeneous means that all the terms have the same degree in each polynomial. Otherwise, it would not make sense to say some polynomial vanishes at some point. Because of this equivalence, you have to take homogeneous. Anyway, these are small details. So what you need to remember is that varieties here are also defined by vanishing of polynomials. Now, these projective varieties are in fact locally affine varieties. That means that at each point you have some neighborhood such that that neighborhood is just an affine variety as I defined before. So that's why this is quite similar to defining manifolds in differential geometry. However, the big difference with differential geometry is that in the world of differential geometry, all manifolds look alike locally. They are just some open disks. But in algebraic geometry, this is completely different. 2 points may not look the same locally because of singularities. You can have singularities which complicates everything. So the picture in algebraic geometry is much more complicated. Anyway, now at least we know what our main objects are. In algebraic geometry, the main objects are varieties, whether they are affine or projective, or maybe open subset of them. So that's the main object. And then the goal is to understand the geometry of these varieties in a local and also in a global sense with respect to polynomial functions. So in other words, we want to classify this kind of objects. That will be like the ultimate goal of the subject. Essentially, that's the ultimate goal of any field in mathematics. You have your main objects, and then you want to classify these objects. Because usually that's just not possible. What you need to do is some kind of very rough classification. Just put your object into different groups so that any two objects in the same group share a lot of properties. And that's what also happens in algebraic geometry. Okay, so we know what varieties are, but we also need to know how they are related, so that we can say what should be similar to what. And for that, we need to understand what maps are in the world of algebraic geometry. But first, we notice that any variety X has a kind of topology, which is quite different from most other topologies that we see in mathematics. Here, the closed subsets of a variety, they are given by vanishing of polynomial equations. So in other words, they are just other varieties or union of varieties sitting inside your X. Now we are working over the complex numbers. We get also a topology coming from the complex numbers, but these two topologies are very different. They are related, but they are very different. And then maps between two varieties, there are two kinds of maps. One I just call maps, another one are morphisms. They are also defined by rational functions or by, so here rational function means quotient, like fractions of polynomials. So everything has to be defined by polynomials. That's what we need to remember. Both the varieties themselves and also maps between them, somehow they should be defined by polynomial equations. Now, if we have a map from X and Y, we say that this is birational if it has an inverse map. I will give you examples. And if we have from X to Y, we say that this is an isomorphism if it has an inverse morphism. Now you see that we have two notations here. One is an arrow and another one is a broken arrow. So the broken arrow means that this map, in fact, may not be defined at every point, but it's defined on most points. However, if it's just a straight arrow, that means that the map is defined everywhere. Let's not go into these small details, just see some examples. If we look at P2, then I can define a map from P2 to P2 given by this formula. I take every point A0, A1, A2 to the point where I raise every coordinate to the power 5. You can take any power, 10, 1 million, or whatever. You get a map from P2 to P2. Now this is a morphism because it's happened to be defined everywhere. But I can define another map from P2 to P2 where I just reverse. I just take the inverse of each coordinate. So A0, A1, A2 goes to 1 over A0, 1 over A1, 1 over A2. you see that this is not, strictly speaking, is not a polynomial, but a fraction, a quotient of polynomials. And quotients are allowed in algebraic geometry. And this map is not defined everywhere. There are points where you cannot map it to any other points in P2. In fact, already in this setting, just P2 maps from P2 to P2, which in this particular example happens to be birational because you can obviously see that this map has an inverse, which is actually itself. Itself is its own inverse. If you look at the set of all such maps from P2 to P2, then you will get a large set. You get, in fact, a group. And understanding the structure of this kind of group is actually quite complicated. And that leads us into group theory. If there is any time at the end of the lecture, I will talk about this in more detail. Anyway, so we know what algebraic varieties are. We have some idea what maps are in algebraic geometry. Everything is about polynomials. Then we come to singularities. And that's why this is quite different from differential geometry, because we have singularities. Just show you some examples of singularities. Here we have two different equations, f t2 squared minus t1 to the 3 and t2 squared minus t1 to the 3 minus t1 to the 2. These are two equations. Both of them give you what we call singularities at the origin. Now these are defined over the complex numbers, but we can't draw the picture here over the complex numbers, so we just draw the picture over the real numbers. And if you just look at the picture, you can, just by looking at it, even if you show it to a child, they will know immediately something is strange at the origin in both cases. So that's why just by looking at pictures, at least in the classical world, people could guess that there is something going on. And you can, in fact, formulate this precisely, that there is a singularity at the origin. And in this case, what happens is that if you take the partial derivatives in T1 and T2, in each case, these partial derivatives vanish precisely at the origin. And that's basically give you the definition of what a singularity is, at least when you have one equation. If you have more equations, the definition is quite similar, that you need to take this partial derivative for all the equations involved. So that's quite interesting, that there is something intuitive and geometric which can be formulated in a precise algebraic way. And then studying the behavior of this kind of singularities can lead you to really very beautiful ideas, even though this is a local picture, but it in fact is strongly related to global geometry. Okay, now if we have a variety without singular points, then we say that this variety is smooth, and this is more similar to manifolds in differential geometry. In fact, if you have anything smooth, you can view it as a manifold. Now, singularities are complicated in general. There are some classes of singularities that they behave very well, and they are in fact very important in modern algebraic geometry, but at least traditionally people have tried to get rid of singularities. And there is a very important result of Hironaka, which says that if you have any variety y, then you can get rid of its singularities in the sense that there is a projective birational morphism. Now let's not worry about what projective means. There is some kind of birational map morphism from some other variety x to y such that this x is smooth, although y has singularities, but x is smooth. So this just this can be constructed by a precise process where in each step you try to make the singularities a little bit better. Then finally you will end up with some x which has no singularity at all. So the proof of this is of course quite long and complicated, but this is a very useful result in algebraic geometry. So it's natural then to try to focus on smooth algebraic varieties rather than singular ones. And that's what people have done for ages. Now, to go any further, we need to also define some other objects. For every smooth variety X, even normal, I don't define what normal is, some kind of singularities. This kind of varieties all have something that is called a canonical divisor, and this is denoted by Kx. And this Kx is the divisor. By divisor, I mean the zeros and the poles taken with appropriate multiplicities of a top degree rational differential form. Now, what that means is that I'm assuming, at least for now, that X is smooth. So this just looks like a manifold. In fact, it's a complex manifold. Then you have differential forms locally. You can define them in the sense of algebraic geometry locally, but also in the sense of complex geometry, differential geometry. Now, if you take these differential forms, and if you take wedge product of them, you can form differential forms of higher rank, of higher degrees. And you can do that up to the dimension of X. So let's say if you work in dimension 1, here by dimension, you can just understand it in the sense of differential geometry, that locally the disks are of that particular dimension. Then you can take these wedge products just by taking, just like in calculus, you have a differential form and you take wedge product with another differential form. That's how it works in algebraic geometry. And then if you take a top degree differential form, you define it locally, then it gives you a rational differential form. That means that it may not be well defined everywhere. And then you can associate zeros and poles to that differential form. It gives you some object which we call a canonical divisor. Now, if we go a little bit more advanced, then the sheaf associated to this canonical divisor is precisely the top degree wedge product of the sheaf of regular functions, regular differential forms. Now, let's just look at some examples instead of these abstract definitions. If I take Pn, then the canonical divisor of Pn is just minus n minus 1 times h, where h is a hyperplane. By hyperplane, I mean it's a variety defined by a linear equation. For example, if you just take the set in Pn where the first coordinate vanishes, that is a hyperplane. So this is very concrete. That's exactly the canonical divisor. And now, if I take a hypersurface inside Pn, by hypersurface I mean a variety defined by one polynomial of degree, let's say r, then the canonical divisor of this hypersurface can be calculated again using that hyperplane. You just take r, which is the degree, minus n minus 1 times the hyperplane intersected with x. It will give you something inside x, and that's exactly the canonical divisor. So, of course, if you have a variety that's defined by maybe 2 equations, then you can at least try to iterate this process. At least it works in some cases, that you can directly calculate this canonical divisor. So at least if you remember P and this hypersurface example, I think that's already maybe good enough. Okay. Now we come to dimension 1. So with all this background that we have, we want to see what happens, how this classification theory works if we go up according to the dimension. We start with dimension 1 because dimension 0 is kind of trivial, just points, but dimension 1. So suppose that X is a smooth projective variety of dimension 1. This kind of varieties are also called curves traditionally. So a curve is just a variety of dimension 1. Now, X happens to be unique in its birational class. And what that means is that if you have a birational map from X to any other smooth projective curve, smooth projective variety, then that will automatically be an isomorphism. So that means that you don't have much room to maneuver here. It's quite rigid, that this shape that you have doesn't really, you can't modify it so much. In a sense, that's good, because that means that the picture is simpler. Now, how to classify then this kind of objects? So by the way, since we are working over the complex numbers, these are also exactly the compact Riemann surfaces. So you can see them in a quite different angle. Now, to classify these objects, we define a number which is called genus. The genus of X can be defined in many different ways. G is either given by sections of the canonical divisor or by, so these are all cohomology, I don't go into the thing, or in a much easier way, this is the number of holes in X, where we consider now X as a compact Riemann surface. So this is a topological invariant, and the picture topologically for X is one of these cases. We have infinitely many cases depending on how many holes you have. So if G is 0, the genus is 0, that means that you just have a sphere. If genus is 1, you have a donut. If genus is 2, you have donut with 2 holes, and so on. So for every G, you have one of these shapes. So topologically, these curves are actually very simple. This is just what I've written here. This picture is a topological classification of this X. However, their algebraic geometry is much more complicated, because you have, for example, infinitely many different X, such that topologically they all look like a donut with a hole. But in the sense of algebraic geometry, they are completely different. They are not the same. So we need a finer kind of classification. So the G is not enough, although that's a very good kind of invariant that can distinguish between different kind of curves. Now, one interesting thing is that there are 3 different, quite different classes. When the genus is 0, that exactly means that your canonical divisor has negative degree. And by definition, you can take this as a definition. That means that X is a Fano. And there is only one possibility, which is just P1. But if G is equal to 1, degree of K is 0. That means K is Calabi-Yau, or more traditionally, this X is called an elliptic curve. And if the G is more than or equal to 2, degree of K is positive, and this X are called general type or canonically polarized. So although there are infinitely many different G, but there are 3, in the sense of geometry, there are 3 different classes. Because, for example, if you have curves of genus 5 and 1 million, somehow they are similar, although they are not isomorphic. Now, we can study this kind of X individually, but also in families. And that's what Riemann did in the 19th century. He showed that if you take all the curves of a fixed genus G, and the G here is at least 2, then they are parameterized by points of some space. So these are usually called moduli spaces. By points of a moduli space M, and this M happens to be also an algebraic variety. And its dimension is exactly 3G minus 3. So this is quite important, because you are putting all the curves of a fixed genus into a family, and each one corresponds to a point on some space, and that space itself happens to be something in the world of algebraic geometry. So you can again apply techniques of algebraic geometry to study these moduli spaces, which then tells you something about how these curves can behave in family. Much later, maybe almost a century later, Deligne and Mumford, they show that this moduli space can be compactified. So in the case of Riemann, this is not a compact space. But Deligne and Mumford show that this MG can be compactified by adding some additional kind of curves with some kind of very mild singularities. So what they say is that if you add some kind of new curves to your collection, then you get a compactification of that space which parameterizes all these curves, with the old ones, the smooth curve of genus G, and also the new one. That's important because, as I said before, in algebraic geometry and generally in geometry, you like to have compact spaces because they behave much better. So very roughly, that's the story of curves. This research started in the ancient world in a sense, but it was intensified in the 19th century, and up to now, this is still a hot area of research. So classification of curves is still not a done subject. Okay, we don't have that much time actually, so I will maybe have to go a bit quicker here. Now then, let's say you know what happens in dimension 1, and then you want to see what can you do in dimension 2 and higher. People already tried in the 19th century to study surfaces. By surface, I mean a smooth projective variety of dimension 2. Now, the picture here is much more complicated than in the case of dimension 1. One reason is that each surface is birational to infinitely many other surfaces. So the picture is not rigid as in the case of dimension 1. So in a sense, if you take an arbitrary x, there is maybe nothing unique about it. That's why it's very hard to classify all of them together. One reason for this problem is related to the canonical divisor, because its degree is usually not uniformly negative or trivial or positive. In the case of curves, the degree of k is uniform. It's either negative, trivial, or positive. But when you go to higher dimensions, this is not the case anymore. Now, the idea, what people found out by trial and error, by just experimenting with a lot of examples, they found out that what you can do here is to transform your x into something else, so that something else has a strong geometric property, that there is something unique about it. And what they came up with was that if you start from your x, there is a sequence of birational transformations such that out of finitely many steps, you get some new variety y, which happen to be again smooth and projective, such that this y satisfies one of these properties. That the k, the canonical divisor, is either negative along some fibration, or it is trivial along some fibration, or if these two cases don't happen, then k is completely positive everywhere. And so that means that this y is actually something very special. It's far from an arbitrary kind of x. And the idea, of course, is to try to classify the y first, and then go back step by step so that you can say something about x. So that's how this works. Now, this process of taking these birational transformations, the whole thing is called the minimal model program, or the classical minimal model program, or MMP for surfaces in dimension 2. Now, after you have found your y, then you want to study the y in more detail. You want to know as much as you can about them. For example, you try to form their moduli spaces, similar to the case of curves. In the case of curves, we fix the genus, and then we say that there is a moduli space. But for surfaces, this is much more complicated because there are many more different possibilities for y. For example, you can have abelian surfaces, you can have K3 surfaces, you can have all kinds of Fano varieties and so on. So you have more classes, and you need a lot more to do in order to, for example, construct their moduli spaces. But anyway, these were, at least the minimal model program part was well understood in 19th century and early 20th century, but still this is ongoing research. People are still trying to study the y and, for example, construct their moduli spaces and so on. Okay, and then what happens in dimension 3 and higher? Already Fano in the early 20th century, he studied varieties of dimension 3. So he already went beyond surfaces. But of course, I mean, he had a lot of interesting ideas, but the technology wasn't there quite to do many things. So it took many decades until people started to get a better picture of what happens in dimension 3. In the 70s, there was an explosion of activities. On the one hand, in the Russian school of algebraic geometry, Iskovsky and Menin, they basically looked at the works of Noether, Fano, Segre, and other people from 19th and 20th, early 20th century. They found gaps. Their arguments were usually not very correct, but they had good ideas. So they used these ideas to prove something rigorous, precise. In particular, they found a counterexample to the Lurus problem by showing that threefold quartics, these are hypersurfaces of dimension 3 given by a polynomial of degree 4, that they are not rational. That means that they are not birational to projective spaces. So that was already a very important development. But on the other hand, in Japan, Itakura tried to classify algebraic varieties according to their Kodara dimension. This is also some kind of number attached to each variety. He also at the same time tried to understand open varieties. By open, I mean non-compact varieties, and he tried to relate them to their compactification. And that was quite important because that finally led to the theory of pairs, which is quite important in modern algebraic geometry. Now, so all this happened in the 70s, interestingly. In a quite different direction, Mori proved the conjecture of Hartshorne, which says that the projective spaces are the only smooth projective varieties with ample means like positive tangent bundle. The tangent bundle is the dual to the sheaf of differential forms. Now, this was important, but much more important than the conjecture itself was the technique developed by Mori in the proof of this conjecture, which is now called the bend and break technique. And finally, this led to his theory of extremal rays and also to a formulation of the minimal model program in higher dimension. So a lot of things, there were other things going on in the 70s, which I am not going to talk about. But in the 70s, 80s, and early 90s, there was a quite well-developed picture of the classification theory in dimension 3. Now I want to formulate what that picture was, so I will define some classes of special varieties. If I take X to be a smooth or with some nice kind of singularities projective variety X, then I say that X is Fano if its canonical divisor is negative or anti-ample, for example, like the projective spaces. We say X is Calabi-Yau if K is trivial, for example, like abelian varieties. And this X is canonically polarized if the canonical divisor is ample, so it is positive. This also corresponds to the notion of curvature in differential geometry. The Fanos have positive curvature, Calabi-Yau's zero curvature, canonically polarized negative curvature. So the signs reverse. Now I just quickly give you these two examples. The second example we have seen already, so I don't go through that. But the first example is just to take a hypersurface X inside Pn of degree R. In this case, any hypersurface of this form is one of these three cases. And that just depends on the degree. If the degree is less than n plus 1, you have Fano. Degree exactly n plus 1, you have Calabi-Yau. Degree more than n plus 1, you have canonically polarized. So the importance of these classes, these special classes of varieties, are that it happens that everything else can be built from them. So in the next few minutes, I try to tell you how this works in higher dimension. In a way, this is similar to the case of dimension 2, but way more complicated. So suppose that we start with X, a smooth projective variety of any dimension. Then we like to run a minimal model program similar to the case of surfaces. And that should give us a sequence of birational transformations. And in each step, we know what happens. We know there are a couple of different possibilities, and we understand these possibilities, basically. There are, for example, divisorial contractions or flips, and so on. This is just a generalization of the classical MMP for surfaces, but the surface case was very simple. The possibilities you get in each step, for example, to go from X to Y, there was, in each step, you had to do one thing, and it's basically the same in every step. And that operation is quite simple, but in higher dimension, this involves much more complicated stuff. Anyway, in the end, assuming that we have everything here working, what we expect is that this Y should be very special in some sense, that either it should have a Fano vibration, or it should have a Calabi-Yau vibration, or if not, then this Y should be canonically polarized. So you see how this is related to the previous page where I defined Fanos, Calabi-Yaus, and canonically polarized. So this picture is telling you that any arbitrary algebraic variety can be, in a step-by-step way, reconstructed from a collection of Fanos, Calabi-Yaus, and canonically polarized. So in principle, if you understand these three classes very well, then at least in theory, you should be able to understand all other algebraic varieties. Of course, not in a simple way. Now, running the MMP requires a huge machinery, and this involves many local and global ingredients. So proving that each step works is quite complicated. One of these ingredients is that in each step we can like we're starting with X, we do something, and then the fact that we can continue again and again, we need something which are called existence of contractions, and this was established by Kawamata and Shokurov already in the 80s. Another thing that we need is that flips exist. And this was established by Mori in the 80s in dimension 3, by Shokurov in dimension 3 and 4 in a much more general setting. And finally, by work of Heiken McKinnon, and in the end, Heiken McKinnon, myself, and Cassini in every dimension. Now, to prove that flips exist, what you need to do is to work out a local version of the following statement, which itself is global version is already quite interesting, which says that if you take all the powers, multiples of your canonical divisor, and take their, so this, I should take H0 here, this is a typo. Should take the global sections of these sheaves, and if you put all of them together, you get a graded algebra, and this algebra happens to be finitely generated over the complex numbers. So this is an interesting thing, but it also happened to hold in the local setting. You can formulate it in a local setting, and one of these formulations is exactly equivalent of existence of flips. Now, a historical summary of what I have already said is that in dimension 1, we have Riemann and so on. In dimension 2, we have people from the Italian algebraic geometry school, and then Zariski, Kodara, Shafarevich, and so on. In dimension 3, we have Kawamata, Kolar, Miyaoka, Mori, Reed, Shokurov, of course, Fano, Hironaka, Itaka, Iskosi, Manin, and many more people that are not mentioned here, unfortunately. And in higher dimension, we have myself, Cassini, Heiken, McKinnon, after works of Shokurov, and of course, many more people, but there isn't space here to talk about these things. Now, I am more or less out of time. Is this 1 hour only?
It's up to
Okay.
Up to Jinjong, maybe a few minutes we can add.
Yeah.
Yeah,
Okay.
we can extend several minutes. Yeah, I think.
Okay. Let me try just to say one more page and then I will finish.
Okay, thank you.
Okay, so suppose that we have done all this MMP stuff and so on. By the way, that's still not complete. A lot of things are left to do, but suppose that we have already done those things, at least partially we know that everything exists. And then the question is, of course, what you do next. You start from X, you get Y, now what can you do with Y? Whereas before, as in the case of surfaces, we want to classify this kind of Y. For example, one way of doing that is to form their moduli spaces. However, doing this also requires other very difficult statements. One of these statements was proved by Heiken, McKenna, and Zhu. They show that if you look at all the canonically polarized varieties Y of a fixed dimension D, and also you fix the volume. By volume, I mean this top intersection number, where you can define it in terms of integration, then these form a bounded family. So bounded means that they can be parameterized by point of some maybe large variety or union of finitely many varieties, but it's not infinite dimensional. So that's the important thing here. This is similar to the case of curves where we fix the genus of a curve and I say that by Riemann we have a moduli space. So the first step here in high dimension, this first step is much harder than in dimension 1. You need to show that they form a bounded family, and this was proved by Heiken, McKenna, and Zhu. So the canonically polarized are one of the outcomes of the minimal model program, but we have other possibilities. We have Fano's, we have Calabi-Yau's, and so on. And for the Fano case, one of my results say that Fano varieties of fixed dimension and with some bounded their singularities, they form a bounded family. So then you can go from here to try to do moduli. Also, in the case of Calabi-Yau's, Calabi-Yau varieties of fixed dimension polarized by some ample divisors of fixed volume. So similar to this case here, you need to fix the volume here. They also form a bounded family. So here, these results tell you that there is now a good basis of going from here to do moduli theory. But on the other hand, work of Kolar, Alexeyev, and other people, they have developed a general theory of moduli of algebraic varieties. That means that they tell you if you have this boundedness, if you have the machinery of minimal model program and so on, then you can go from there to form moduli spaces. Now, if you combine all these things together, then what we get is that moduli spaces exist for canonically polarized varieties and also for polarized Calabi-Yau varieties, and in some sense also for Fano varieties. But in a very different direction, many people have also worked on constructing moduli spaces of a specific kind of Fano varieties. They are called K-stable Fanos. So this is a different line of research, although it intersects with what I have said so far. So there are many names here. They have tried to construct moduli spaces of those specific kind of Fano varieties, although this is a quite different moduli space, but still it's in the same direction that you have a class of objects and you want to parameterize them and find moduli spaces for them. Okay, thank you for listening. I will stop here.
Okay, thank you for your talk. Maybe Jin Jung will make an announcement for the next talk.